Hello everyone, my name is Noor Khutaba, undergraduate scholar, Department of Software Engineering in Haliç University, Istanbul, Turkey. Today I will be presenting my research paper Context about strategies classification for EV charging. For introduction and motivation, as homes adopt more solar and wind energy, managing EV charging became more important to avoid peaks and make better use of renewables, instead of using complex optimization methods. We approach the problem more simply by classifying each charging session into one of four strategies based on the EV's urgency and available renewable energy. This gives us a lightweight and practical way to guide smart home charging decisions. For problem statement and objectives. Residential EV charging is typically uncoordinated, which leads to avoidable peak loads, poor use of on-site renewable, and frequent violations of local grid constraints. While many existing solutions rely on complex optimization models, those approaches are often too computationally heavy for real-time use on edge devices. What's missing is a simply interpretable mechanism that can translate the current EV charging needs and renewable conditions directly into practical charging strategies. Propose a four-class option taxonomy that captures both EV urgency and the availability of renewable energy. Build irreducible machine learning pipeline using conceptual EV BV wine features. Evaluate multiple classifiers to determine which model is the most stable and reliable. Integrate the final classifier into a lightweight HEMS control strategy that can be deployed on low-power hardware. Solution: we solve EV charging coordination by introduction a lightweight strategy classification system, a four-class taxonomy, urgency, multiple, renewable availability, is predicted using conceptual EV BV wine features. Random forest classifier produced a strategy which is directly executed by a rule-based HEMS controller, enabling real-time, interpretable, and edge-friendly EV charging control. Related works. Most existing research focuses on forecasting EV charging demand, PV wind generation, and deep learning-based energy management. Common methods include spectral clustering, LSTM, GRU, and transformer models. HEMS studies typically optimize renewable use with PV battery systems or probabilistic AI-driven control. However, none of those work propose strategies classification upward that combines EV urgency with renewable availability or provides direct deployable HEMS charging actions. This gap motivates our proposed classifier. System architecture. Input data sources. EV sessions look combined with PV and wind generation profiles. Future engineering a comprehensive set of temporal user behavior, charging rate, and renewable context features. ML pipeline, a streamlined process consisting of data imputation, scaling, feature selection, and classification. Predictive model, the classifier outputs one of the four proportional clauses, each repeating a distance EV charging strategy. HEMS control model, a rules-based scheduler that applies the model decision while respecting traffic, carbon intensity, feeder limits, and user mobility requirements. Dataset description. We use the IEE data port, EV charging, and DG output dataset, which provides two EV session types, high and low urgency, plus hourly PV and wind generation profiles. EV records include arrival depot times, SOC, battery size, preferences, and implied charging power. The renewable dataset offers daily and inter-day PV wind distribution. Together, those allow instruction, both urgency and renewable availability levels. Model and methodology. The target class is defined as class equal to 2. Multiply urgency plus renewable, cipher 1, 2, 3. Our workflow includes pre-processing, implementation, scaling, and MI past future selection. K equal to 25. Future engineering, temporal factors, charging behavior, energy need, user preferences, and renewable. Statics, PV, wind balance, competition, thresholds. Model testing, Random forest gradient boosting expertise, SVM, Canon, logistic regression, MLP, decision, 3 native PIs, leaking safe training and cross-validation hypermeter award evaluation. Evaluation metrics: accuracy, balanced accuracy, macro precision, recall, F1, Matthews correlation coefficient, MCC. Those metrics ensure fairness across all 4 classes and repentance against positional imbalance. Results: best performing model, random forest, 80-20 split, accuracy 86.8%, balanced accuracy 86.8%, macro of 1 86.9%, MCC 82.1%. Observation: logic regression performs subordinate clause with much lower computational cost. Renewable future application reduced RF macro of 1 by 5.1%, proving their importance. The classifier remains stable across different renewable trials, 50 to 60% more. This diagram shows a smart home system where EV charging data plus solar and wind data are processed. Features are engineered. Then machine learning models classify the charging need. The predicted class sent to the HEMS scheduler, which schedules EV charging optimally based on cost, carbon intensity, and system constraints. Target class description across the 4 urgency renewable categories. Average test accuracy and cross-validation performance for all evaluated models. Test accuracy of all models across different train test split equations. Model performance across train test splits. This is confusing matrix for random forest and gradient boosting models. High performing models, AUC up to 0.98. ROC compression showing top performing classification models. Top feature from random forest with total renewable energy as the strongest predictor. Analysis and insights. Renewable context features total renewable wind average are among the most informative. Charging rate and energy need features align well with urgency classification. Random forest provides the strongest correlation across split and results. The 4-class taxonomy maps cleanly to HEMS actions and allows real-time on-device control. The approach balances model interpretability, performance, and computational efficiency. For conclusion, this work introduced a practical, interpretable, and deployable ML-based strategy classification approach for residential EV charging under PV wind availability. The 4-class taxonomy and engineered features enable high accuracy classification while respecting grid and mobility constraints. The classifier maps directly to actionable HEMS policies without requiring complex optimization models. Future work: integrating uncertainty-aware or practical levels, developing end-to-end optimization models combining traffic, carbon intensity, and feeder limits, real-world deployment with HEMS telemetry and dynamic traverse, adding battery storage congestion and community-level energy sharing, extending the taxonomy for V2G enable strategies. Thank you. I want to thank our supervisor, Dr. Mohammed Al-Hubaishi, for being part of this journey and helping me in this success. Team members and Halley University for their support and encouragement throughout this research program. For any questions, please email me at my email. Thank you, everyone. Noor Khatwa.